Today, we are very excited to have Jai Moondra as our guest speaker. Jai is a fourth year PhD student at Georgia Tech, where he is advised by Swati Gupta and Mohit Singh. His research focuses on discrete optimization and its application to algorithmic fairness, combinatorial learning, and quantum computing. His thesis explores how to design algorithms that balance multiple objectives, including fairness and online learning. Today, he has very kindly agreed to give a talk titled New Approaches to Multi-Objective Optimization and Application to Fairness and Online Learning. So join me in welcoming Jai and over to you.
Yeah. Thanks everyone for being here during the holidays. I'm sorry this is that this is during the holidays, but thank you so much for joining. So yeah, I'm going to talk about multi-objective optimization with applications to algorithmic fairness and online learning. And this is joint work with a lot of people, but the majority of it comes from three of my papers, which are with my advisors Swati Gupta and Mohit Singh, and another fellow student at Georgia Tech, Hassan Mortagi. Yeah, and very briefly, I'm going to explain what I do. So one of the things I do is approximation algorithms with non-standard objectives, non-linear objectives, and then a lot of machine learning and the intersection. There's algorithmic fairness. An example question would be how do we cluster points fairly? Then there's the component of online learning, and an example of a question there would be can you speed up an algorithm like projected gradient descent or any iterative algorithm over specific polytopes. I do a little bit of quantum computing where I try to design algorithms that individually can beat either classical or quantum computing algorithms. And finally, I work a little bit in quantum noise reduction. Today, I'm going to focus on the machine learning and the approximation algorithms part, and with specific focus on multi-objective optimization. And what are the kind of questions I'm going to look at? So here are the two broad set of questions I want to address, right? So suppose you have some domain of feasible solutions. Of course, if you're given an objective, we can optimize over it and so on. But when you're given multiple objectives, which can happen in many settings, how do we trade off between them? What does it even mean to trade off between them? And the second is, given that you already know the optimal or the approximate solution for a given objective, and you're given a new objective, can you warm start the first one, and can you basically achieve the new optimal faster? And here's an example, right? So suppose we are just doing linear optimization over a polytope. And for those three different objectives, in those three different colors, you'll have different optimal points, and an algorithm returns to you those points. And now maybe one of the challenges is to understand if there is a single point that is optimal for all of them. In this case, there is. And what happens if you already know the optimal for example, the green one and the blue one, because the pink objective is sort of a convex combination of the two. Can you say something about the pink objectives optimal? So this is just like a toy problem, which illustrates what sort of ideas I'm going to present. Right. Here's a brief outline of the talk. So I'm going to start with what we call fairness portfolios, and its connections to multi-objective optimization. And the second half of the talk is going to be more about online learning on combinatorial polytopes, where we discuss a different trade-off between two different objectives. So I'll get started with the first one. So let me speak about facility location and clustering problems, right? So this is a report by the United States Department of Agriculture, and there have been several such reports in many different parts of the world, which basically say that some facilities are underrepresented in certain areas, so people have to travel much further to get groceries or something, and these things are also present in almost all areas of the world. And here's another one about medical facilities, which is about drugstores in the US. And so the question is, all right, so there's a problem in the placement of facilities, but what can we do about it? So of course, as computer scientists, we might want to make things fairer and recommend that, all right, like open facilities here and everything's going to be fine. So, all right, here's another example where this is a map of the state of Arkansas in the US, where we map medical deserts, which are areas that are a certain distance further away from their nearest pharmacy, and also poorer. So these areas are called medical deserts, and as you can see, they disproportionately affect majority Black populations. So again, there's unfairness here, and there are economic disparities and so on. So these things are very well documented. And so, how do we open facilities in a fair way? And these questions can be asked anywhere. Algorithmic fairness is a huge field, and you can ask these questions in workload balancing. You can ask these questions, of course, in machine learning. So the first thing to say is that a lot of people are trying to answer this question, right? There are about 200,000 results on Google Scholar. In philosophy, this question has been discussed extensively. And for facility location problems alone, this is a list of 20 different FAIR objectives from 1994. So the standard approach seems to be that people try to come up with a FAIR objective and then say that this is how we solve for this FAIR objective, the corresponding optimization problem. But of course, the issue is that we don't really know which of these is fair. If we had a definition of fairness that was universal, that would be great. But how do we how do we sell this to a policymaker who might want to place facilities in a fair way, right? So different people disagree on what's fair. So for example, let's take the store example. I just want to do clustering. I want to open a hospital here, and the city is divided between two different groups. And if I open a hospital there by prioritizing the average person, I might get accused of discriminating against the green group. Let me prioritize the furthest away person, something like a case-centered problem, and then we immediately see the issue that it's very far away from where most people live. So different people disagree on what's fair, and very well-intentioned notions of fairness may have very unintended consequences. And finally, it is very difficult to translate legal fairness principles into mathematical models, right? So there are many issues with coming up with a definitive fairness objective. And so how do we make decisions? This is a central question we want to ask. So let me start by saying that, all right, I'll go from the spectrum between prioritizing the average person to prioritizing the furthest person. I'll start at the optimal solution for the first one. And as I move along this, my optimal solution is going to move, right? That's very standard in multi-objective optimization. So of course, I might have a large number of different solutions as I go from the left to right. But let me pick only two solutions out of these infinite number of solutions. And what are the guarantees that these two satisfy? The guarantees that these two satisfy are that no matter which objective you pick on that number line, one of these two solutions is guaranteed to be, say, almost optimal for that objective, right? So for everything on the pink in that number line, the pink solution is going to work. Everything in the blue solution is going to work. There is still going to be a trade-off between the two, but you can basically uh, position this to a policymaker and say that this is the essential trade-off. And now you might want to select between these two instead of coming up with a mathematical notion, which might be difficult for a policymaker, right? And so here's the formal definition. So we are given a domain of feasible solution that I'll call D. We are given a class of objectives that I'll call C. And I'll be given an approximation ratio alpha. And here's the formal definition. So I want to find the smallest subset of D that alpha approximates all fairness objectives, right? So if I choose any objective F and C, this might not be working. I should have that the optimal within the set S is within factor alpha of the optimal within set D. So here's an example with a linear optimization problem again. So I have those three different points that are optimal for these three different objectives. But I want to claim that this blue point is going to approximately satisfy all of them, right? Like we can just draw these lines and see that. And so maybe the blue point basically tells you the essence of the problem. You have these three different objectives that are competing, but the blue one is basically good for all of them. And there is a special name for this sort of phenomenon, very well studied phenomenon. When you just have one solution that approximates everything well, then it's called a simultaneous alpha approximation, and there are well-established theorems for this, right? But it gets much trickier when you want more than one solution, or there's an alpha where you can't find a single solution that alpha approximates everything. And there are new algorithmic challenges in dealing with that, and I'll try to go over some of them. So our setting will be that we'll think of the cost vectors as d-dimensional vectors. So think of d individuals, and you have some cost on all of them. So think of in clustering problems, you might have that different people have different distances to the nearest facility. Or in scheduling problems, you might have different loads on different machines and so on. And our fairness objectives, the set C is going to be norms on RD, right? So for example, if you take the L1 norm on a cost vector, then minimizing the L1 norm is the same as minimizing the total cost. And minimizing the L infinity norm is the same as minimizing the maximum cost. And there's, of course, a trade-off between the two. But this trade-off you can basically represent by extrapolating between the L1 and L infinity norm, which you can do using these LP norms and as I'll define later, top K norms, ordered norms, and so on, right? But we'll always assume that these norms are monotone, as in if someone's cost increases, your overall cost does not come down. So that's a natural assumption. The second assumption we are going to make is that all of these are symmetric, which we define as invariant to the permutation of coordinates. So if I exchange the identities of two people, then you should not have that the cost in those two cases is different. And this is a natural assumption that follows from a lot of philosophical principles, but also it makes our life easier because without this assumption, things get much more difficult. Our aim is to come up with a small number of solutions, and we'll restrict that small number to be polylog in the dimension. And recall that for most combinatorial problems, the set D is going to have an exponential size, right? And so even getting something that is polynomial in D is a priori difficult, but we want something even better than that, right? We want polylog in D. So, all right. Yeah. Right.
So it's linear in D is moving. It means report every.
Right. So the set D may not be given explicitly, right? For example, let's take K clustering.
Polytope.
Right. It could be a polytope, the vertices of a polytope. So in K clustering, you have n choose K solutions. So you don't know them explicitly.
Also, this is confined to minimizing. Maximization, the story would change.
The story would change. So the definition would stay the same or analogous, but maximization problems seem to be much harder. Maybe I'll try to comment on that near the end.
Generalized P norms as P means rather than norms.
Precisely. And exactly. And it seems like they behave very differently from LP norms in terms of generally also, but also in terms of this particular problem. Yeah. Right.
Say that at least if you assume, for example, norms or even concave functions, which are these properties that you mentioned, then you are able to again get good approximation, but they're used, for example, in this simultaneous alpha. But here, like what you're saying is I want not a single solution, but a set of solutions such that one of them, say, alpha majorizes it. So this is sort of the
right. Right, exactly. So we are going to use majorization arguments. And so our guarantees would be that, all right, you have a set S, and no matter what other vector you pick, one of these majorizes that vector. Yeah. So those are exactly the sort of tools we are going to use. Yeah. So, all right. Let me move forward and talk about norms now. And so over the last 10 years or so, a very rich theory of norms and the classes of norms has developed. So there is, of course, the L1 and L infinity norm. Recall that L1 is just the sum. So almost all problems that you see in combinatorial optimization are one of these two, right? Minimize the maximum cost to minimize the sum of costs. So almost all minimization problems are going to look like this. Then you have LP norms, which of course go between L1 and L infinity in a smooth way. And a lot of theory is also developed on minimizing. Given an LP norm, tell me what the optimal solution is or what the approximately optimal solution is. There's top K norms, which are relatively more recent, where the top k norm of a vector x there is the sum of its highest k coordinates. So the down arrow there represents you've basically sorted the vector x in a decreasing order. And so now you're looking at the cost of the k most affected people, right? And of course, if you just choose k equals 1, then you record the L infinity norm. And if you choose k equals d, the dimension, then you just have everyone's cost. So this is also another way to go between L1 and L infinity norms. And in some sense it's more fundamental than LP norms, and I'll come to that. Then there's a larger class of norms that people have studied, which are these ordered norms. This time again, I sort my vector x in a decreasing order, but I have these weights. So the highest weight I'm going to put on the person who's bearing the most cost. The second highest weight I'm going to put on the person who's bearing the second highest cost, and so on. So clearly these generalize top k norms because I can choose the first k weights to be 1 and the others to be 0. So you get this Venn diagram, and our original class of norms of symmetric and monotone just has everything here. So why should we even study top k and ordered norms? Why not be happy with LP norms? So one of the important issues that comes up, and we started with LP norms, was that when we spoke to anyone who's outside theoretical computer science, they would say, but what does an L2 norm mean? Or what does an L3 norm mean in terms of fairness, right? So top K norms are much more interpretable, ordered norms are much more interpretable. This is one practical reason, but there are more theoretical reasons too. So in one of the classical theorems on simultaneous approximation, Goel and Meyerson in 2006 proved that, all right, if you want a single solution to be alpha approximate for all, then it is sufficient to prove it for top K norms to be able to prove it for all symmetric monotone norms. So it's a very interesting property which allows you to go between top K norms and symmetric monotone norms. It is precisely majorization. Yeah, it is basically just taking the majorization argument, and it's a restatement of that. Yeah,
Symmetric.
that are one homogeneous, or actually all symmetric monotone norms. Um,
I mean, we can talk at least for the majorization result.
right.
To need which maybe like the norms would satisfy.
They actually do satisfy. Yeah, that's right. Yeah, yeah.
So you do need one homogeneity.
You do need one homogeneity, and all of these norms actually by default satisfy that. Yeah. So in fact, this result holds for a much larger class of symmetric convex functions, sure convex functions, precisely. Yeah. Yeah. And another nice thing about ordered norms is that you take any symmetric monotone norm, you can approximate it by an ordered norm by a factor log d, which is tight, but it's another interesting result and a very recent one. Another nice thing is that, all right, every symmetric monotone norm is the supremum of a certain set of ordered norms. So ordered norms and top k norms seem very fundamental to the study of symmetric monotone norms, which is a much general class. And so with all of these nice properties, one might wonder if everything can be reduced to top k norms, in particular that second property. So alpha approximation, if you want a simultaneous one, then it's okay to study top k norms versus symmetric monotone norms. But when you increase the size of the portfolio to more than one, right, which we are going to do, that property breaks down, meaning it's no longer sufficient to have a portfolio guarantee with respect to top k norms to extrapolate it to symmetric monotone norms. So that's the interesting technical challenge here. So let me phrase this question. So I'm given a set D. What is the smallest size of an order one approximate portfolio for various norm classes, right? So I want a portfolio that is a constant factor approximation for all norms in that class. What's the smallest size I can get? Let me try to convince you first that the answer is actually order log D for LP norms and top K norms. And this is a nice simple argument that has been present in various forms in literature.
So you just have to go to log D and it approximates all till L. Like, just do it for L1, L2 till L log D. And all the subsequent are another in a constant.
So that is precisely the idea, except that you can't go integral because L1 and L2 themselves might be off by factor square root d. Yeah, so you have to do it a little bit finer argument. So that sort of argument is actually present in a 2008 paper, but let me present a different argument for the same thing, right? So I'll present the argument for LP norms. The same argument holds for top K norms. So given any norm, so given a P, let me denote the optimal cost by opt P. And opt P is a non-increasing function of P, well, because LP norms are decreasing in P as you increase P. And finally, the L1 and L infinity norm are within factor D of each other, right? And so let me just draw this curve and let me start at P equals 1. And each time my value halves, I'm going to pick the corresponding optimal solution. So for P1, I'll pick the optimal solution, put it in my portfolio. Next time the value halves, I'm going to pick that solution, put it in my portfolio, and I'll keep doing this, right? When the value decreases by a factor at most D, so I can do this at most log D times. So and then you can show that this sort of portfolio would be sufficient because you're sort of continuously varying this thing, right? And yeah, as I said, for LP norms, this follows from a different argument. And this technique was first introduced for top K norms by Goel and Meyerson. This sort of generalizes to very different settings. And what we proved was a slight extension of this for the first part of the theorem, which is to say that any norm class that basically goes between L1 and L infinity in a nice way, in a monotonic way, you can basically get an order log size portfolio. Or if you want an alpha approximation, you can do order log d to the base alpha. For facility location problems, of course, you can't pick the optimal solution because it's NP hard to do so for each of these LP norms. So you can relax the alpha there, and you can just get an order one approximation. So and all of these are tight, even for facility location problems. So the story is sort of open and closed for these norm classes. And just to illustrate how this sort of thing behaves in practice, we suggest location of 25 new pharmacies, and basically you're fine with 3 solutions, then you can notice some differences between these 3, right? So the third one prioritizes facilities in the north and so on. And so in practice, policymakers really like this because they can basically pick among these 3 options, right? And so story nice for LP norms and top K norms. For ordered norms, we jump from log D to polynomial in D. And that is also not trivial, although it follows from an argument by Chakrabarti and Swami in 2019. In the interest of time, I'll not go through that argument, but poly D we show is essentially tight, meaning that there are you cannot basically pick log D solutions to satisfy all ordered norms. You do need a polynomial number. For symmetric monotone norms, it was unknown what the right answer is. We showed that the answer is polynomial in D. It's a slight extension of the argument for ordered norms. So all right, and yeah.
The practical happens so thing that you D is very small, right? It's just 2.
So
the ambient dimension.
So the ambient dimension is something like 30 because we look at like demographic groups.
Okay, I see.
Yeah.
So it's a feature.
Yeah. But in practice, so in theory, the answer is log D, but you can in practice do much smaller than that because it's a planar problem and so on. Yeah. Right. So the answer is polynomial in D for ordered norms and symmetric monotone norms, which is not good because these bounds are tight. But then, of course, the next question is, can you find specific problems where you can reduce this polynomial in D to polylog D? And I will try to illustrate a couple of examples and sort of a new technique where now this is a counting problem instead of just an optimization problem. And I want to say that a lot of the classical primal dual arguments or anything in approximation algorithms, you can extend them not just to finding the optimal, but to counting the number of solutions. So, right. So let me go over a simple toy problem, right? So I'm just given a bunch of machines, D machines. They have different processing times. And I want to allocate n identical jobs to these machines. So I'm going to say that the load xi on the machine I is the number of jobs allocated to I times the processing time. And minimizing the L infinity norm is the classical make span minimization or max load minimization problem. minimizing the L1 norm is the total load minimization problem. And of course, if you want to minimize the total load, you're going to put everything on the machine that has the smallest processing time, right? So that's trivial. And let me convince you that you cannot find a single solution that will satisfy both of those objectives. So here's an example. So suppose that you have the number of jobs is equal to the number of machines, n equals d. The processing time on the first machine is 1, and the processing time on every other machine is square root d. So now, if you wanted to minimize the L1 norm, the total load, you're going to put everything on the first machine, and you will have the total load of d. But then that means that you're putting the maximum load is quite high, right? It's d. You can of course get a maximum load of just square root d by putting one job on each machine. And these are basically incompatible. No matter what combinations you try, you're going to fail. And the best simultaneous approximation you can achieve is of the order of square root d. So you can't even achieve a better than square root d approximation for just these two very simple objectives. So what can you do with more than one solutions, right? So here's our theorem.
It's tight.
Square root d is tight, yes.
Always find.
Yes, of course, yeah, because you can always pick the L2 norm solution, I think, yeah, and that would work for all norms, yeah. And that's right for not just this problem, but in general for any problem, yeah. So let me state this theorem. It seems very involved, but think of alpha as a constant greater than 4, and we will give you only log d solutions that alpha approximate, that constant factor approximate all ordered norms. So from one solution doing a square root d approximation, you now go to constant factor approximation by just log d solutions. And this is sort of tight because the lower bound is log d divided by log alpha plus a small log d factor. And so this looks very complicated, but what it looks like is basically this. So on the x-axis, you have the approximation that you want, and on the y-axis, you have the size of the portfolio. So if you want a constant factor approximation, our upper and lower bounds are basically off by a factor log d. If you want a log d factor approximation, then our upper and lower bounds are basically tight, and so on for a polynomial approximation, which is what a single solution achieves. Remember, so there's a single solution there that does everything. And let me try to present an argument for this, right? So remember, we are doing ordered norms. So you have given a bunch of weights, W1 through WD. And you're looking at minimizing the ordered norm of a vector x. So I'll just write an integer formulation. So the load on machine I, xi, is the number of jobs assigned to I, that's ni, times the processing time pi. The total number of jobs you need to assign is n, and each of these must be integer, right? So we'll do the standard thing. We'll say that, all right, let's relax this to a continuous problem, and here's what we get. So xi over pi is the number of jobs, total number of jobs is n. So this is very standard, right? And now let me make this claim. Whichever machine has the smallest processing time, the optimal solution must have the most amount of jobs assigned to that machine. And this follows from the majorization argument that you had mentioned. So this is a simple claim. But what this does is something very neat. So notice that this is a norm minimization problem. So it's a convex problem. Your polytope, the optimal can be anywhere on the polytope, right? Like in the middle of the polytope or something. But what this allows you to do is, this allows you to convert this problem into that formulation where you say that I'll only look at solutions that satisfy this claim one property where x1 is more than x2 and so on, right? That is very nice because now recall that ordered norms just weight the highest cost by W1 and so on, and so it becomes a linear problem, which is amazing because this polytope has d plus 1 constraint. So one is the hyperplane constraint, and then the d minus 1 inequality constraint, and then there's a final inequality constraint. It has d plus 1 constraints. If you want a vertex, d of them should be tight, and so you get basically d plus 1 solutions. So you at least have a portfolio of size d plus 1, and it's very nice to work with this set, right? Because you can explicitly write down what the solution is, each of the vertexes. It's going to have the form, all right, some of the machines are going to have load, some load, equal load, and everything else is going to have load 0. And the final claim is that, okay, we are at D plus 1, we are at D, and so we can go to log D by this, by just like a standard sparsification or a doubling argument, the kind I presented earlier. I'll omit the details. And this very simple sort of argument, mainly claim 1, basically tells you that there's a portfolio of size order log D. So things work out very nicely here. And let's see what happens if we try to, I should mention that this was only for non-integral allocations. So if you want integral allocations, claim 1 does not hold, and you have to be a bit more careful, which is very low as a factor 4. So you can't get optimal. So now let me introduce a different problem. Let me try to do this for general polytopes, right? So let me have a covering polytope ax greater than or equal to b. And I want to minimize a norm here and recall that I need a bunch of solutions that approximate all norms. So we have a convex formulation. Suppose we knew what order the optimal for any fixed W satisfies, right? Suppose we knew that order, then once again, we can replace it by a linear problem because that's how ordered norms work. And that would again be very nice because now you're working with the vertices of the polytope instead of the whole polytope. And so your optimal portfolio size would be the number of such possible orders pi that for any W might be optimal times the number of vertices in the problem on the right, T pi. And like the previous argument, we might get a nice number. Let's see what these numbers are. Of course, the number of orders is D factorial if you don't do anything else, which is already worse than the polynomial in D bound that you have generally. So we are already really far away. And the number of vertices of P pi, now there are not D plus 1 inequalities, but well, suppose that A has R rows, and so you'll have R inequalities there, and there's another D of those. So you have R plus D, choose D, which is roughly D to the R vertices of P pi, which is also bad because that's at least a polynomial in D. And so overall, you get something really poor. And so how do we go from something that's exponential in D to polylog in D, right? And I want to convince you that, of course, that for constant R, you can actually do that. The first argument I'm going to make is a sparsification argument. So I'm going to say that, all right, let me group columns of A that look similar, and let me discard very, very small entries. So this is a standard sort of argument that's present in these sort of works. And by doing that, you at least bring the number of distinct columns in A to log D to the or to the order R, and maybe think of epsilon as a constant for now. So you went from a large number of distinct columns, which is maybe D to the R or something, or D columns, to log D to the order R columns, which is very nice. So think of N as the new dimension you're sort of working in, because that's the number of distinct columns in A, right? And each column corresponds to one entry of your vector X. And now let me define this polytope. Yeah.
So then multiplicative, like, so will violate AX greater than or equal to B by some multiplicative, or will you sort of scale it down to?
Right.
Okay.
Yeah. So you lose a factor 1 plus epsilon in the process. Yeah. Yeah.
And this is not like Johnson-Lindenstrass or something where you're projecting down in here. This is some other.
Yeah. Yeah.
Okay.
So I've omitted the details, but something like Johnson-Lindenstrass would not work because that would be a randomized reduction.
Yeah.
And because our problem is convex, that you typically can't use any randomized reductions.
Yeah, I was wondering if, like, instead AX greater than or equal to B, you project down, like have a like apply some projection, like you just yeah. I mean, instead of sparsifying the columns of a project, like it's a dimensional reduction argument, but maybe smarter than.
Right.
Yeah.
Yeah. So JL was one of the tools we tried, but the kind of guarantee we wanted was deterministic, and that is the only reason why we could not use that directly. Otherwise, you would, of course, have that directly, and it would be much nicer. Yeah. 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 So So we have this sparsification argument. It's maybe a little tricky, but it's not anything that's non-standard. So far it's all along expected lines that we are doing, right? Now let me define the polytope d pi, where now let me pick orders not on all d numbers, but like on these n numbers, capital N numbers, and let me say that this polytope d pi is the set of all vectors that satisfy this order pi. Now already the number of orders is capital N factorial, which is roughly log d to the power order r square, because n itself, remember, was log d to the order r. So the number of vertices is bounded. The number of orders is still n factorial, which is bad, but the number of vertices is bounded. So here's the effective dimension, and let me say that again. So the number of vertices is nice because that's polylog in d for a constant r, but the number of orders is still an n factorial, which is actually a polynomial in d to the r. So even if your r is constant, you're still at a polynomial number of vertices, polynomial number of orders. And so here's the final trick where we say that, okay, let me not count the number of orders in a primal problem. Let me define a proper dual problem, and let me count the number of orders in the dual problem. Now, of course, I'll need to define a mapping between orders in the primal problem and the dual problem, but let me say how to do that. Here's the key idea. So you want to count orders in an appropriate dual problem, not in the primal problem. So let me define a dual problem, which at first glance doesn't look like a dual because these are both minimization problems. But here's the dual. So I want to minimize lambda transpose A and the dual norm of this ordered norm, subject to the constraint that lambda is in the probability simplex. So the entries basically sum to 1. And let me try to convince you that this is actually the right dual, even though it might not appear that way. And so here's the lemma. The optimal primal value times the optimal dual value is exactly 1, right? So how do I do that? I'll start by this product of the ordered norm of x and the dual norm of lambda transpose A. I'll apply the standard Cauchy-Schwarz. So I'll just get the dot product of those two. That's lambda transpose AX. And because AX is 1R, so I can just assume that the column B is just a bunch of ones by rescaling and so on. So that's just lambda transpose 1R, which, because lambda is in the simplex, it's exactly 1. So at least I hope I've been able to convince you that this product is at least 1. And showing that it's exactly 1 requires like a standard argument using Lagrangian duality and so on, but that can be shown too. So we have a nice dual problem, and this problem is nice because the ambient dimension here is d. The dimension there is r, and recall that we are thinking of r as a constant. So now our dual problem is in a constant dimension, where hopefully it's much easier to count the number of things. We were counting the number of orders in the primal, but we're going to count something different in the dual. And here's a key lemma. So the number of possible optimal orders in the primal. So as you vary W, you're going to get different orders for the optimal. I want to say that that is at most the number of possible regions that capital N choose to hyperplanes partition the simplex into. And what's the sort of idea behind this? The idea is that, all right, the orders on optimal X, they correspond to orders on the dual optimal lambda transpose A. And so you need to consider hyperplanes of this form, where the ith entry of lambda transpose A is equal to the jth entry of lambda transpose A, and there are clearly capital N choose two pairs because we are working in capital N ambient dimension in some sense. And so now this becomes a problem, a geometric problem, where you are asking how many hyperplanes or how many regions can I divide the simplex into by these many hyperplanes, and that's like a simple geometric argument. You can show that if you take t hyperplanes, and if you take any polytope in r dimensions, you can divide it into at most t to the r minus 1 plus 1 regions. And this number is slightly better than the trivial bound that you can get. And it requires a little bit of care, but it's not a whole lot difficult. Oh, I see. I did not know there was a name for this. I see. I'll definitely look that up also. Yeah.
Yeah. For it.
I see. Okay. Yeah. That's very interesting. I had no idea about it. Yeah. And so this is the theorem we get, right? If you want a constant factor approximation with R constraint, you get a portfolio of size log D to the order R square. That is constant factor approximate for ordered norms. For symmetric monotone norms, you get a slightly worse approximation. And I don't know if this can be improved to order 1. So the upshot of all of this is that uh, you can not only do the standard primal dual optimization thing, but you can essentially count things between primal and dual. That's maybe the main thing, that main technical contribution that we had here. So right, in the few minutes I have left, I will try to quickly go through a completely different setting. But I want to say that this is motivated in a very similar fashion to what we previously had, which is fairness and so on, right? So this setting happens quite often in learning problems where you have. Yeah.
Big approximation is when you're talking about this Venn diagram of norms, there were these approximation guarantees. So log D just comes from the fact that ordered norms log D approximate.
Precisely, yeah.
Okay.
We don't know how to tackle symmetric monotone norms directly, because a key step was converting the convex problem to a linear problem by assuming an order, and we don't even know how to write a symmetric monotone norm parametrically. So we don't know how to do that. Yeah.
But I mean, this I understand this is not the key concern here. Like, how do you how do you do the actual when you solve the problem, you do need to solve it for certain instances, right? So
Right.
what are those optimization for? Like, maybe the easier way of asking the question is, so you do have this result, but there is a portfolio size log D. How do you, let's say, computationally, how do you find this?
Right. So as long as you can optimize for a given ordered norm, you can convert the whole thing into a polynomial time algorithm. And so if you have an alpha approximation for optimizing for a fixed ordered norm, you get a factor, you get worse by a factor alpha. So the whole thing is every step that I said can be converted into a polynomial time algorithm. Yeah.
So you look at the partitions it generates for everyone, you find the corresponding date vector, you solve the timer and include that in your.
Right. So I did not go through how to map primal solutions to dual solutions,
Yeah.
but that can also be done by basically when you do the Lagrangian duality, it gives you exact conditions for how to how to take a dual solution and convert it into a primal solution. Yeah. So I did omit that part. Yeah. So let me go through this setting here where, all right, so I'm given an optimization problem over some polytope or a convex body, right? And now I perturb the objective a little bit. And so I get a new objective, and then I perturb it a little bit and I get a third objective. And why would you want to do that? Like, think of iterative optimization algorithms where in each step you are basically, for example, projecting a different point. So these are perturbations of the original problem, right? And typically people use black boxes to solve all of these, right? And yeah, here's the iterative projections example. Think of an algorithm like projected gradient descent, where what are you doing? Well, you're playing a point xi, and then you move in the direction of negative gradient. You get to a point outside the polytope. You want to come back in the polytope, so you project back on the polytope, right? And the next time you move again and you project back again. Now these iterates become closer and closer. So one might expect that the projections of two consecutive iterates are kind of going to be similar. So why do you want to spend the whole time again doing a new optimization problem? Maybe you can reuse information from the previous projection, right? And this is a natural idea. Uh, and I'm going to speak specifically about the projections and how you can use these to really speed up, both empirically and in theory, these iterative algorithms that do these projections. But let me first quickly do the online convex optimization setting. So you have a convex body P and a time horizon capital T. And so at each time you want to play a point X T in the body, right? So what do you mean by play? You just output that point. And then once you have output that point, a convex loss function ft is going to be revealed, and you incur loss ftxt. So some other point would have maybe incurred a smaller loss, but well, you didn't know the function ft in advance, so you have to kind of adapt by looking at these losses that you incur, right? And the goal is to minimize the regret. And the notion of regret is, let's say you look at all of your losses, and now you look at any fixed point that could have, what could a fixed point have done, right? And the difference between your losses and anything that a fixed point can do is your regret. And this is a very powerful sort of framework. And as it turns out, you can actually design algorithms that do something non-trivial just with this setting, nothing else. I will not go into explaining those algorithms, but I'll just give an example of why this might be useful in machine learning. So suppose you have n products on an e-commerce platform, right? And you want to order them. Each time a new user comes, you want to say, this is the order, I display these in. And how is this an online convex optimization problem? Well, think of all the permutations. Each permutation is a ranking. And if I take the convex hull of all of these permutations, then I get my polytope and I want to play a point in this polytope, right? So this is one example of that problem. And this is the kind of nice polytope in 3 dimensions. If you have 3 products, those are the 6 points you could play. Simple. Uh, and that brings me to submodular base polytopes. So we assume that the polytope we are working with is submodular base polytope. So all of the matroid polytopes are submodular base polytope. The problem that I just mentioned is a submodular base polytope over a permutahedron. And very quickly, the definition of submodularity, it's a set function defined on a ground set E. And if you take any sets A and B and evaluate the function on A and on B and add them up, and then evaluate it on their intersection and union, well, the original values are going to be greater than the values at intersection union. And it's present in a lot of combinatorial problems and so on. Satisfies many nice properties. And I'm going to work with the base polytope associated with the submodular function. Let me spend a minute on this. So what's the base polytope? So you're looking at the set of all vectors in R to the E, so the dimension of the ground set, such that for each set S, when you add up the coordinates of the vector in that set S, that's what I mean by XS, that is at most the submodular function value at f of S. And for the whole ground set, you should have that the coordinates add up exactly to f of E. And the problem I previously mentioned of ranking in recommendation system is actually this problem. So you're just playing points over a submodel base polytope. And these satisfy very, very nice properties. They're very beautiful objects studied very well and so on. But note that the number of inequalities there is exponential because the number of subsets of the ground set is 2 to the n if your ground set size is n. And so it's not easy to work with these directly. Online convex optimization, let me come back to this. There are 2 broad set of algorithms that are developed for these. One is mirror descent and its variants. So projected gradient descent is an example of mirror descent. They have a very nice regret guarantee, which is actually optimal. So you can, after t time steps, your regret is only some constant times square root t, which is interesting. You don't even incur linear regret. But the bad part is that they require one projection step, projected gradient descent, in each iteration. Then there are these other set of algorithms that are called Frank-Wolf and its variants, which have worse regret rates, right? So you have t to the 2/3, which is more than t to the half, but they require only a linear optimization. And linear optimization is quite fast on base polytopes and many other polytopes, as one might expect. Projection is a quadratic problem, linear optimization is a linear problem. And so the question is, and that's a computational bottleneck. And so the question is, well, can you speed up projections in mirror descent to get the best of both worlds? So I want the regret of mirror descent, but hopefully the runtime of Frank-Wolf and its variants. That would be great, right? We would have the best of both worlds. So we'll not quite be able to get the runtime of Frank-Wolf, but we'll be able to significantly reduce the runtimes of mirror descent and its variants. So what can we learn from? So here's the learning part. So as I mentioned, because you're projecting in each iteration, maybe you can learn from the previous projections. But also, how are you projecting? Projection itself requires some algorithm, right? Some offline optimization algorithm. And that algorithm, if it's an iterative algorithm, will have its own iterates. And as you come closer to the optimal, you might be able to learn from these iterates of the offline optimization algorithms themselves. So there are 2 ways you can learn from your past, essentially. So I maybe in the interest of time, let me skip the finer details and let me just say that convex optimization over submodular based polytopes is a very combinatorial sort of problem where you can reduce it to what your gradient space looks like. So if hx is the function you're optimizing over, then the gradient at the optimal has this very nice form where some of the coordinates are just going to be exactly equal, some others are going to be higher but equal, and so on. And for the set S1, you're going to have a tight equality there. Recall that there's like a less than equal to here, but exactly at the coordinates where your gradients are equal, you're going to have a tight equality. You're going to have another tight equality when more gradients are equal, and so on. Of course, you have everything. You have a tight equality when you take all the elements, right? And so you can start thinking about convex optimization not in terms of um, continuous nature, but you can start thinking of it as, okay, can I obtain these sets S1, S2, and so on? And just obtaining these sets is enough for you to do the convex optimization. So you've converted a more of a convex optimization problem into a combinatorial one. Um, and here's the main idea. So let me not go into the finer details, but let me say something like this. Suppose you have an iterate where the gradient values are the one present in sort of teal color there in the middle of those bands. And now I know that this iterate is not very far away from my optimal. I'll have that guarantee from an iterative optimization algorithm. So if I'm not very far away from the optimal, well, whatever variation I have in each coordinate, if I have the guarantee that the first two elements in S1 there, they're never going to be able to exceed the elements in S2 there, right? So no matter how bad the variation is, I'm always going to be the element E1, the value is always going to be smaller than the element E3 in the gradient space. That's very nice because that means that the set S1 must be tight. You can show that. Essentially, you obtain information about the tight equalities in your optimal by not even having reached the optimal. And when you do this, then you basically can guarantee that, all right, I already know enough about the optimal, and maybe I'm able to round much earlier than I would otherwise round. Uh, and that sort of gives you this. We have like a bunch of theorems about this is what you can do. But the idea behind all of these theorems, let me omit the details. The idea behind all of these theorems is that you can use a lot of combinatorial structure to speed up what are more like continuous algorithms, such as projected gradient descent and so on. And this is only over submodular based polytopes. There are a large number of combinatorial polytopes that we do optimization over. Typically, we use them, continuous algorithms as black boxes, but we don't have to do that. We can basically utilize tools from combinatorial optimization to speed things up. Let me not go through this quickly. This is the algorithm that looks kind of complicated. Let me just quickly say how our experiments do. So we do. So we are comparing everything against the green line, which is projected gradient descent with an optimization algorithm that is itself based on Frank-Wolf. And what we see is that the runtimes come down by a factor, by a 3 or 4 orders of magnitude, or in this case, it's 2. In different experiments, it's 3 or 4, simply by reusing information from previous iterates. And that brings it much closer to the runtimes of the fastest algorithms that I previously mentioned. So you have been able to maintain the same regret, the optimal regret, but your runtimes have come down by 3 orders of magnitude or more. And this holds, so this was over the permutahedron, which is the rankings, but you can do this over other polytopes and we get similar results. Yeah, so to summarize very quickly, I presented something about multi-objective optimization, a bunch of problems which come essentially from 3 of our papers. Uh, uh, and yeah, I do think there are many more ideas that can be developed even more here and a bunch of open questions. But thank you so much for listening, and I would be happy to take any questions if there are. Yeah.
the jobs are not of full length.
Right. So we expect that in the general setting, you do have that the portfolio size cannot be better than polynomial in D. That's our conjecture, except uh, we don't know how to prove that yet. Yeah. Right. So I think a lot of the arguments are extendable to very simple settings where the deadlines maybe are. Um, so let me try to get this right. Where
Not jobs are flexible at great jobs, but they are not available at any
Online and
but they are coming complex streaming.
I see. Uh, yeah, that's an interesting question. I don't know the answer to that. I don't know if these techniques will extend directly, um, or if there would be a lower bound in terms of the portfolio size. Right.
There are ACM of which also does compare with your. So where does your technique falls the with respect to the ACM information? It makes sense.
Uh, I'm not super familiar with the techniques there, but let me give a vague answer to that question, which is that a lot of the multi-objective optimization settings try to either combine the objectives in some way, or they try to find a solution that works for all objectives. And once again, like with the caveat of not knowing the techniques in Bayesian optimization, uh, I, the difference here seems to be from many other settings is that uh, we we do optimization with respect to all objectives, but we allow more than one solution. Yeah. Yeah, sure. Right. No, so yeah. So so two columns I'll call similar if they're multiplicatively within 1 plus epsilon factor each entry. Right. Right. So it won't be tight. For example, you can always choose n equals capital D because there are only D distinct columns. So at some epsilon, you will be able to basically just have all the columns distinctly and not do that sort of thing. Uh, I guess as if you allow D to grow and epsilon to also become smaller, right? Then I believe this is tight because this is simply saying that once you discard small entries, let me just count how many possibilities there are. Like the column has R different rows. So for each row, maybe like let me just count how many possible entries there are in that row. This is just that sort of counting argument. So it's log D over epsilon to the power, the number of rows, basically. Yeah. Oh, thank you so much.
And let's proceed to CSA Gardens for lunch and more discussions.